Okay, so it is recording now. Welcome everybody to this session of the GravBR project. Today we have the pleasure to have Professor Elisa Ferreira that will be speaking from Germany. And for those of you that don't know Professor Elisa, she has done her undergraduate studies as her master's studies at the University of São Paulo. And the PhD she obtained from the McGill University in Canada under the supervision of Professor Robert Brandenberger. And then she moved to the Max Planck Institute for Astrophysics, where she is now at least affiliated to. And during this, during the end of between the end of the PhD and moving to Germany, she got a position at the University of São Paulo as a professor. So she's now a professor at the University of São Paulo, and I guess she'll be going back to São Paulo at some point in the near future, if the pandemic allows. And so Professor Elisa is very active in the research of dark matter in particular. Recently, I think it was put out last year, she wrote a review on the topic of this seminar, and it was now accepted for publication in the Astronomy and Astrophysics Review. Also, it was quite recently that this was announced. She received the very prestigious grant by the Instituto Serrapilheira in Brazil. So it's quite nice that people doing research in this field are getting the money to carry out the research. So it is really a great pleasure to have Professor Elisa here. And with that, I stop now and give to Elisa the stage. So thank you very much, Elisa, for giving the talk. And I will just shut up.
Thank you very much for this really nice introduction. And thank you for the invitation. It's really a pleasure to be contributing to the GravBR, which is an amazing initiative. So congratulations for it. So today I'm going to be talking about this topic of research that I've been dedicating the last years, which is ultralight dark matter. I today want to give a review about those topics so you can understand why I am so excited, and maybe everybody in the field of dark matter is so excited about these types of model. But if you already see me talking about it, I'm sorry, it's going to be a little bit repetitive, but we have some new results also towards the end. So not only I plan to give a review on these topics, but also present some bounds on those models and show you guys that we are being able now to narrow down a little bit the possible masses allowed for dark matter if we have it to be ultralight. So I don't think I need to convince any of you about the existence of dark matter. So as we know, the evidence for dark matter, it's huge and it comes from many different scales. So we have many different observables and many different probes that show us the existence and the need for a dark matter component. And each of these evidences tells us a little bit about the properties of dark matter. So not only they tell us about the necessity of having a dark matter component, but they always tell us a little bit about the properties that dark matter might have. So it's very important, dark matter, it is one of the most well-measured problems or mysteries in cosmology, but this also allows us to measure it quite well, the properties. So as our observations improve, especially the observations on large scales, we were able to build the standard model of cosmology, which is the lambda CDM model, which is a very successful, so it is observationally is very successful. We can really constrain the parameters of this model with sub% precision. And it is a description of our universe that describes our universe with 6 free parameters. And in this model, in the lambda CDM, which is very precise model for the description of a universe, dark matter is described as this cold dark matter fluid, so the CDM fluid. So what we know about dark matter mostly today comes from these large scales, come from these measurements of these large scales, which tells us that dark matter is described by this fluid, which is cold, which means that it moves much slower than the speed of light. It is pressureless. It clusters in all scales. It is dark, so it doesn't interact or interact really weakly electromagnetically. It is collisionless, so there is no self-interaction, or the self-interaction is very, very small. And we know the abundance of dark matter today, so we can explain the structures that we see in our universe nowadays. And lambda CDM, and especially the CDM paradigm, it is very successful, as we can see here shown in the matter power spectrum, which is the 2-point correlation function in Fourier space of the density or of galaxies in the universe. And as we can see here from this curve, which shows many different observables, in many different scales. This spans 4 orders of magnitudes in scales, which describes roughly the evolution of 14 billion years of our universe. We can see that CDM and lambda CDM in the case describes quite well this model. So it's a very successful model, and it really describes quite well how dark matter should behave on large scales. However, on small scales, there's still room, so we don't have the precision of the measurements that we have on large scales to really tells us that the properties of dark matter are well known. So we also don't know much about dark matter. First, we don't know what dark matter is. Second, because of this lack of precision, or I would say less power, less precision that we have on the observations on small scales, we actually can relax a little bit of all of these properties that we have for dark matter on large scales. So we know that those properties should hold on large scales because they really reproduce the power spectrum and other observables quite well. But on small scales, you can relax a little bit. So it doesn't have to be completely cold. It could be warm. It doesn't have to cluster in all scales. It could have a small non-gravitational interaction or even a self-interaction. So this allows you to build different models of dark matter that allows you to have different behavior for the matter power spectrum here on small scales while maintaining the CDM behavior on large scales. So the small scales are still weakly constrained. So they allow us to really think that all of those, the CDM paradigm could be relaxed on small scales. Another thing that tells us that maybe CDM can be relaxed on small scales, or maybe CDM needs to be complemented, has different properties on small scales, are these small scale problems or small scale curiosities for who do you ask, which are basically mismatches between, or incompatibilities between, what you see in simulations of dark matter from what you measure in the universe. So for example, we have the cusp core problem that tells us that if I do simulations with dark matter only, what I predict for the density of dark matter in the radius of the halo of a galaxy, of the dark matter halo of a galaxy, is that this halo will have a cuspy profile, so it will diverge for small radii. radius. But when we measure this, when we see galaxies, when we observe this, we actually see a chord profile that tends to a constant. So this is the cusp core problem. There are other problems like the missing satellites or many other of those problems that nowadays we really don't think they are problems, but they are definitely some things that we pay attention. One of the most interesting of them, in my opinion, are those called regularity and diversity of rotation curves, because they tell us that although galaxies in our universe are extremely diverse, so they come in different shapes, different masses, they span a huge amount of different masses, they're extremely regular. And this regularity of those galaxies, it is encompassed in those scaling relations, like, for example, the baryonic Tully-Fisher relation. This is one of the most known, but you have many others. And the baryonic Tully-Fisher relation tells us the relation between the baryonic mass that we see in galaxies, that we measure in galaxies, versus the circular velocity. And each of these points is a different galaxy. And we can see that not only this doesn't agree with what is predicted by lambda CDM simulations, it has a different description. It has a different law here, power law. It goes to V to the 4. But that is not the most important characteristic. It really shows a very tight relation. So this relation is so tight that the dispersion is smaller than the error bar of each point. So this is very interesting because those galaxies are so different. They have so many different properties, but they are very tightly correlated, the baryonic mass and the velocity. And this cannot be explained by CDM. There are some explanations for these small scale problems. So probably most of them can be solved by including baryons in your simulation. So this incompatibility appears because you only have dark matter in those simulations. And of course, baryons are going to play a huge role. So nowadays we have a huge advancement in those simulations that really show that most of those problems can be solved by the inclusion of baryonic feedback. But it is very challenging, for example, to reproduce this tight correlation that we have here in the baryonic Tully-Fisher relation. So this is still an open question, but it is a very fast-moving field of research, and probably feedback will be very important for that. Some other people suggested that maybe we have to modify the Newtonian dynamics to describe the behavior of dark matter on small scales. And this comes with the name of MOND that most of us have heard. And most of us also know that it doesn't work, at least the vanilla MOND, or maybe the extinctions of MOND, because it doesn't describe, it describes a universe without dark matter, only a modified modifying Newtonian dynamics. So you modify gravity. And it is incompatible with CMB and other large-scale observations. But one thing is very curious about MOND, and this is interesting. So before Milgram described it as a modified gravity theory, he realized that there is actually this empirical relation here that is happening in galaxies. That actually, when you are in environments where you have large acceleration, the acceleration is described by the baryonic acceleration. So this is the Newtonian regime. But when you're in small acceleration regimes, the acceleration is given by this geometric mean of the baryonic Newtonian acceleration and this other parameter A0 that you measure from these scalar relations. And actually, this empirical relation explains quite well rotation curves of galaxies, and also explains those type of scaling relations. So although MOND doesn't work as a modified gravity theory, it is interesting that this empirical relation, it is important. So we'll come back to this. But I think the thing that we can also do, and this is the thing that I focus on, and many of the other models focus on, is that, okay, so we need to have CDM on large scales, but we can have a model of dark matter that behaves like CDM on small and large scales, but on small scales has some modified behavior. So that is a possible avenue for explaining all this. So since we don't know the nature of dark matter, so we don't know what dark matter is made of, but we know that it needs to behave like CDM on large scales, but it can relax this on small scales, the CDM paradigm. Many models of dark matter were created, invoking very different paradigms, very different phenomenon in physics to explain the nature of dark matter, which gives you this state-of-the-art, or this zoo of models of dark matter that we have today. And just to illustrate here in a mass scale, of course, these models have other degrees of freedom, but just to illustrate in a mass scale, I'm sorry. These models, they can invoke things like primordial black holes, which are these huge objects I'm sorry, with masses like solar masses. We can have WIMPs, which are these new particles that have masses of the order of GeV. Or we can even have ultralight dark matter particles, which are the lightest possible particles that can describe dark matter, which will be what we will discuss today. Thank you. I'm sorry. So the possibilities are different phenomena, phenomenon in physics, but also they span very different orders of magnitude. So although we know a lot about dark matter, we know a lot about the properties of dark matter, we still don't know a lot. So there's many possibilities for what dark matter can be. And one of the interesting things that we have been moving forward in the future, in the past few years and in the future, is using the small scales to really try to probe this microphysics or the particle physics characteristics of dark matter. So as our small scale measurements are improving, we are going to be able to probe this characteristic, these different properties of dark matter using small scale observations. Okay, so today we're going to talk about the lightest possible dark matter component, which is the ultralight dark matter, which is around here in the 10 to the minus 22 EV to EV mass range. So the ultralight dark matter are dark matter models that are composed by an ultralight candidate, which needs to be a boson, needs to be described by a scalar field, which is non-thermally produced in the early universe. And we wanted to have a very small mass, around 10 to the minus 22 EV, which is 10 to the minus 57 kilograms, to EV, 10 to the minus 35 kilograms. But why do we want such a light component? Because if you have a particle with such a small mass, this particle will have a large de Broglie wavelength. So the size, the wave description of this particle will have a wavelength, the de Broglie wavelength, which is of the order of parsec to kiloparsec. So if I'm within this range of masses, my dark matter particle has a de Broglie wavelength of the order of kiloparsec, which means that in galaxies, which are hundreds of kiloparsec, it could be like kiloparsec to hundreds of kiloparsec side, this dark matter will actually behave as a wave, because the size of the de Broglie wavelength of dark matter, it is around the size of the galaxy. While if I go to larger distances, if I look from the large scales, I would see this this dark matter particle, although with a large de Broglie wavelength, it will be for me like a point particle. So on large scales, I see these as particles, so I recovered CDM predictions. But on scales of galaxies, I see a modified behavior, and the behavior is modified by this wave-like behavior. This model has many advantages. Not only we can have a particle physics or condensed matter motivation for it, it might address the small scale problems, but it also, and this is, in my opinion, the main reason and the main driver for those models, it has a very rich phenomenology on small scales that comes from this wave nature of dark matter. And there's also a possibility to form a Bose-Einstein condensate or superfluid inside galaxies, which I'll talk a little bit better later. So the phenomenology of these models is very rich, which makes these models not only to give us a lot of predictions that can be tested, but would also allow us to test those models pretty soon with small-scale observations. But there are many different ways that you can build ultralight dark matter models. And in the literature, we have different proposals for how you can have ultralight fields describing dark matter. But you can actually describe them, and you can actually divide them in 3 classes. And this division actually tells us how each of these models behave on small scales. So this division of classes is very instrumental to tell you that each of these models are going to have a very similar behavior and phenomenology on small scales. So the first model that we can, of ultralight dark matter, we call fuzzy dark matter, which is just one of those light particles under the influence of gravity. So I only have 1 degree of freedom, which is the mass. I can add a self-interaction to this fuzzy dark matter, which I call self-interacting fuzzy dark matter. So now I have 2 degrees of freedom. And I can have a completely different model, a third model of ultralight dark matter, which is called dark matter superfluid. And in this model, you still have a wave behavior on galaxies, but this wave behavior has a different dynamics. It has a different effective dynamics on galactic scales that actually reproduce that empirical Mond behavior that I showed you before. So this model not only tries to have a very rich phenomenology, but also is able to reproduce the Mond behavior on small scales. I won't have too much time to talk about this model, and also we don't have a lot of bounds on these models yet. So, but I have slides about it, so you can ask me in the questions. I'll focus more on those models, not only because most of the bounds are in these models, but also because these models have a particle physics motivation. So the axions or axion-light particles can be part of those models. And axions are these particles that we postulate in particle physics to solve the CP problem of QCD. So they have a motivation in particle physics, and they can behave like dark matter. You can also have mod axions produced in string theory and by other mechanisms, and they can have a lighter mass because the QCD axion has a mass around 10 to the minus 6 eV. But you can have lighter axions or axion-light particles. So this gives a very good origin for those models, but you can also have phenomenological models describing these 2 models. So I'm going to focus today more on the fuzzy dark matter and a little bit on the self-interacting fuzzy dark matter. And here I can already tell you why we use the name fuzzy. Fuzzy is really like because you have this wave behavior, so you cannot see quite well, so it's quite fuzzy. So that's why we give this name. Just a curiosity.
Sorry, Elisa?
Yes.
Can I ask a question?
Yes, of course.
I'm just wondering, I mean, if there is a fundamental reason for focusing on ultralight bosons. I mean, so is this just a postulate of the model, or is there a more fundamental reason for that?
So it depends on what you want. For example, if I have a model that predicts axions, and those axions are light, of course, those axions are going to be light. They are going to behave like dark matter. So axions and like axion-light particles they behave like dark matter in the universe. So if you have a theory that predicts those ultralight fields, there's a big chance that they're going to behave like dark matter. But also, you can postulate this as a theory of dark matter and see the predictions and test them and see, is this a good candidate for dark matter, as we usually do for other dark matter candidates. So I think that's one advantage of those models. Not only you have phenomenological models that you can just postulate that dark matter is made of ultralight field and then see what are the consequences, but more than that, axions and axion light particles are predicted in many beyond standard model theories. So if you have those particles there, they're going to behave like dark matter. So it's interesting to know their behavior depending on their masses, their mass range.
Yeah, because I'm just wondering in the following sense. So, as far as I understand, the advantage of this perspective on ultralight particles is that you have the benefits, let's say, of modified gravity or MOND, and also the particle physics picture of
yeah, the MOND
dark
is
matter.
only the dark matter superfluid. Those two, they don't have a MOND behavior. They are going to have this wave-like, this different phenomenology in galaxies,
But for instance, if you started with, instead of postulating an ultralight boson and postulating an ultralight fermion, I mean...
yeah, then you cannot go to those low masses. You have to stop around QeV masses. So you cannot have this, has to be that light, it needs to be a bosonic particle.
Okay.
Yeah. And the beautiful thing is that we have these axions and axion light particles that are predicted in many theories that have exactly this characteristic that we want, and they behave exactly like dark matter because of their masses.
Okay.
So yeah, you can come from both sides. You can come from motivation from particle physics, so I have those things, how they behave, or you can come from a phenomenological side. I want a modification on small scales of the behavior of dark matter. This is one of the ways that you can get.
But then just following up, sorry for the big question.
Don't worry.
If you go a slide back, yeah, so you said that just in the superfluid case, you reproduce MOND.
Yeah.
But in the other cases, I mean, do you have a better description of the rotation curves?
So you describe them as well as you would describe them on CDM, I would say, with the addition of having a chord profile in the center of galaxies, which is something that we also want to have. So yeah, you improve in some things. But yeah, the MOND is only this theory.
Okay. So does it qualify it as better than the others?
It's tough to use this word because you have different phenomenology. And you describe different phenomena. The rotation curve of galaxies is tough because if you ask someone that does those things, maybe they prefer MOND, but then MOND doesn't work outside. But CDM also fits quite well those curves. So yeah, it's tough to say what is better. What those models really provide you is a very rich phenomenology. So many predictions on small scales that can be tested quite easily. Not quite easily, but they are becoming more importantly nowadays. So you can really test if this possibility is true. And since those light particles appear in many effective field theories and string theory and many beyond standard model theories, it's interesting to know the role that they have as dark matter.
Okay, thank you very much.
You're welcome. Maybe this will become more clear when I talk a little bit more about those models. So yeah, so I'm basically going to talk about those models now that are actually, you have a scalar field representing dark matter that is ultralight. So the cosmological evolution of this model is that I have this scalar field in a cosmological background. And this field is described by a potential like this, which has an interaction and also a mass term, which is basically a potential that has this format. So when we say that axions and axion-like particles could be ultralight dark matter, it's because they have exactly this type of potential that those models, ultralight dark matter models, need to have. And what these potentials do is that while the field is evolving as expansion goes, it behaves like dark energy in the beginning. So this field is slowly rolling to the potential, and then it oscillates on the bottom of the potential, and this is where they behave like dark matter. So we can see this better in this slide. So I just dropped the self-interaction term just to make it easier for us to see. So it is a competition between this term and this term. So when the Hubble parameter is larger than the mass, this will behave like dark energy. So we can see here, this is the behavior of the field at early times. And this is the equation of state at early times, that it behaves like dark energy. But as the Hubble parameter evolves and becomes smaller, at some point it's going to become smaller than the mass. And then this field is going to start oscillating. And this means that the average of this equation of state is going to be 0. So it's going to behave like dark matter. So these fields have this behavior. And what tells you if this is going to be dark matter today, behave like dark matter today, is if it starts oscillating before matter radiation equality. So if I have a mass that is bigger than 10 to the minus 28 eV, this means that this is going to behave like dark matter before matter radiation equality. So today it's going to be behaving like dark matter. So this gives you the minimum mass that you have in this model to behave like dark matter. If it is a smaller mass than this, it will behave like dark energy today. So it is only a dark matter component depending on the mass that you have of this field. But in this talk, I'm not interested in cosmological behavior. I'm interested in what happens in galaxies. I'm interested in studying the evolution on small scales. And for that, we take the non-relativistic regime of the previous theory of this Klein-Gordon equation. And when we take this, the non-relativistic regime of that equation, we actually get a Schrödinger equation describing the evolution of this fuzzy dark matter or the self-interacting dark matter, which is coupled with a Poisson equation. So big phi here is the gravitational potential. Psi describes our field, our fuzzy dark matter field. So those two equations are coupled. The Schrödinger equation describes the evolution of the field, and here it is how the gravitational potential depends on the density of this dark matter component. And when we see this equation, we can already see that this is quite different than what CDM is. So it's fundamentally different from CDM, warm dark matter, or self-interacting dark matter, the description. This is described by a Schrödinger-like equation. If I have self-interaction, this term is present. If I don't have self-interaction, this is the fuzzy dark matter case. So it is the simplest case. We can make this change of variables here. So we associate this with a density and a velocity. And if we can rewrite these equations in a fluid description, like a hydrodynamical equations. So the first equation is like a continuity equation. And the second equation is a Euler-like equation. So it's an Euler type of equation. But it has this last term here, which is not present in Euler equation, which is called quantum pressure. This is kind of a misnomer because this was first seen in the context of quantum mechanics, but this would appear anyway, this term, if you have this type of behavior here. And this term actually counteracts gravity. So it is something that fights against the clustering of dark matter. So this term is only present in these models. And with this description, we can see quite well how different this is from CDM. And again, if I have self-interaction, I will have interacting pressure here. And the consequencing of having this quantum pressure term that fights gravity here in the FDM, you're going to have something counteracting gravity, or in the case that you have interaction, you will have something that is either helping gravity or also counteracting gravity. And the consequence of that is that you're going to have a region here where you have hydrostatic equilibrium. This is what defines the Jeans length. And the Jeans length tells us that inside this region, quantum pressure wins. So you have a stable solution and you don't have structure formation. While in regions outside the Jeans length, structure formation will proceed normally as you will have in CDM. So you will have in these models a suppression of the formation of structure on scales smaller than the Jeans scale, which is the scale where those two forces are equivalent. So on small scales, I'll have a suppression of formation of structures. And if I have self-interaction, for attractive self-interaction, this Jeans length or this characteristic length is really small. So I will only have suppressed formation of structure in really, really small scales. So this is basically very similar to CDM. But for repulsive interactions, I can also have a Jeans length that is sizable. And the consequence of that is that I'll have then this, what we call a core. So it is a region where I won't form structures. So where I'll have the density doesn't grow. And we can see that this Jeans length is of order of 55 kiloparsec for a 10 to the minus 22 EV mass. So if I have a mass around 10 to the minus 20 EV, this is of the order of a kiloparsec. So I'll have a suppression of the formation of structures on those scales. And this, the fact that you have this quantum pressure term and this different wave-like behavior is going to give us a very rich phenomenology, and I'm going to show you each one of them. The first is suppression of small-scale structures. So because I have this finite Jeans length, where inside of this Jeans length, so for all the perturbations that are on scales smaller than the Jeans length, I don't have structure formation. I won't have small structures in those models. And you can see that from the simulations. So on top of here, I have FDM, fuzzy dark matter, and on the bottom, I have CDM. And we can already see by eye that the smallest structures here in the fuzzy dark matter case do not appear. But I can also take the 2-point function, correlation function that in the Fourier space, that is the power spectrum. And I can show this here. So here is the matter power spectrum. And we can see here that CDM predicts this blue curve. But since I don't form structure on small scales are here, large scales are here, I'll have a suppression of the power on small scales depending on the mass of this component. Which is easy to see here in the power spectrum. So depending on the mass of my particle, this suppression can be on really small scales, intermediate scales, or even large scales. So those models that have a suppression on large scales are already ruled out by observations, but you can have this suppression on small scales. And this suppression of small scale structure also leads to the suppression of the formation of halos. So the smallest halos, they are not going to be formed. We're going to have a universe that only have the biggest halos. And we can see this in the halo mass function. Halo mass function with respect to the mass of the halo. And if we can see here, for example, for 10 to the minus 22, I don't form halos that are smaller than 10 to the 8 solar masses. So my universe is only going to have the biggest halos. So this is a consequence of the suppression of the small scale that those models have. On galaxies, those models, the suppression also has an effect. So if I want to see this effect on galaxies, we are deeply in the nonlinear regime, so we need simulations to really understand the suppression. And here I'm showing a simulation done by a member of my group, Joette Chen, that we simulate only one halo of a galaxy. And we can see that when this halo forms, we form a core in the middle of the halo. So this means that a core is that region that we don't have structure formation. So we have a fixed density, we have a constant density. And we can see this being formed in simulations. So these models then, they predict this formation of cores. So they predict that our halo of the galaxy is going to have NFW profile in the outskirts, which means that it is described as CDM, dark matter in the outskirts, which is given here in this. But instead of becoming cuspy, as the NFW profile usually tells us, it's cored in the inner parts of the radius. So it's going to have a cored profile in the inner regions of the galaxies, which is something that we see that is necessary by observations. And how do we get this cored profile for dark matter inside galaxies? We get them from simulations because we need this nonlinear evolution. And the profile that we usually use is this one from Schiff from 2014, which is a fitting function for simulations, which tells us how this core profile depends on the mass and on the halo where this dark matter is. And this relation is very important, this relation and this relation, because if I want to use observations of galaxies, for example, or dwarf galaxies to be able to obtain the mass of my fuzzy dark matter, I need to use these formulas that can be obtained only by simulations. Another interesting phenomenology that comes from this model is also wave interference. So as I told you, inside galaxies, those dark matter particles basically behave like waves. So you're going to have wave interference, and this can be easily seen in these simulations that I showed you, where we see here interference patterns, so destructive and constructive interference. We also see that in other simulations. And these patterns, this destructive interference, they are of order of the Berkeley wavelength. So they are very hard to observe, they are very small, but they are very interesting features of these models that really show this wave nature of this dark matter component. Another thing that shows this wave nature of this dark matter component is the formation of vortices. So those models, they predict that you're going to form vortices. Vortices are these structures, these vertical structures that you can have in the halo. This is the figure, the illustration that artistic illustration that I put in the first slide for the vortices. And there are actually sites where the fluid velocity has no vanishing curl. So in those models, you have that those models are basically irrotational. So the vortices are the only place in the fluid where you have rotation is possible. So you can have them in the fuzzy dark matter, or you can have them in the self-interacting fuzzy dark matter, and they have very different structures. But they really show you this is another characteristic of this wave-like structure of those ultralight dark matter models that is not present in other dark matter models. And last but not least, we can have different dynamical effects on these models. And we have many different dynamical effects that can happen. Relaxation, oscillation, friction, and heating. These models have a different prediction for each of these dynamical effects. For example, we can talk about relaxation, which basically is the formation of a Bose-Einstein condensate or superfluid in the interior of galaxies. So those models are basically composed by ultralight bosons. And there is then the possibility that those bosons can condensate and form a Bose-Einstein condensate only through the gravitational interaction. Just to give a small, quick, to remind you guys about Bose-Einstein condensate. So Bose-Einstein condensate are those fluids where when you go to lower temperatures, you have a macroscopic occupation of the ground state. So all the particles of this fluid, when you go to a small temperature, they go to the ground state. They occupy the ground state. And when this happens, instead of you describing these particles as individual particles, you can actually describe them as a collective of particles. And you can describe them by a wave function of the entire fluid, a single wave function of the entire fluid. And this happens when, at least in laboratory, when you have a small temperature, when you get this fluid to a very small temperature. Some fluids can also, they are also superfluids, which means that when you go to low temperatures, not only they condense into Bose-Einstein condensate, but when they condense, they present superfluidity, which means that this fluid flows without friction. As we can see here in this illustration, where this cup, when it reaches here, when it reaches condensation, it starts to flowing outside the cup. So it flows without friction. And the description of this phenomenon in condensed matter, they are described by this Schrödinger equation, this nonlinear Schrödinger equation, which is exactly the equation that describes our ultralight dark matter. So for this reason, there is we would like to investigate the possibility of this forming a Bose-Einstein condensate in this core inside the galaxy. This was first simulated by this group, Levkov, which I show here. So here we have just the halo and these particles under gravitational, under gravity. And if you let it evolve for time, you can see here that they're going to form a Bose-Einstein condensate. And they can be formed in a time, the relaxation time, which is smaller than the age of the universe. So it is possible that you can form Bose-Einstein condensates, which are these amazing macroscopic quantum mechanical phenomena actually in galaxies. So that is, I think it's pretty interesting. I just want to say that this is an open question yet, because those simulations, they use analogous systems. So this is an open question if you can actually form these Bose-Einstein condensates inside galaxies. But this is one of the possible features of these models. I won't have time to talk today, but other dynamical effects is that those models really present a different dynamical friction than CDM, for example, and they can also present some heating effects in stars. So those are basically the phenomenological predictions of those models, which are very rich, and they allow us really to measure and try to look for the clues of these models in small scales and also a little bit on large scales. So now I'm going to show you the observational implications and the bounds that we can put in these models by looking for those predictions using diverse observations in many different scales. So here, today I'm going to show only the fuzzy dark matter bounds. So I'm showing bounds on the mass, because mass is the only degree of freedom of this model. And I'm showing only the fuzzy dark matter because this is the most well-studied model of ultralight dark matter, where we have many, many bounds of this model. And the bounds are presented here. The highlighted regions are the forbidden regions for the mass. And we have this each of these different rows, they present a different observable putting bounds on the mass. And we're going to discuss a little bit of them now. Just a quick reminder that those bounds are obtained by considering that the fuzzy dark matter is almost all or all of the dark matter in the universe. If you relax this, if you say that fuzzy dark matter or ultralight dark matter or axions are only a part of the dark matter in the universe, you can relax those bounds. So those bounds are if we think axions are 100% or most of the dark matter in the universe. So first, let's start with these bounds here. So these bounds, they are obtained by trying to measure the suppression of small scales, trying to see what is the consequence of the suppression of the small scales that we have in different observables. For example, if I have a suppression of small scales, I can measure this using, depending on the mass or depending on where the suppression happens, using the CMB, the cosmic microwave background, and the large scale structure. This puts some bounds on the mass, as we can see here. We can also use Lyman alpha force. So what happens is that, as we said, you have a suppression of small scale structures, so you have a suppression of small halos. So those models don't have the smallest halos possible. And this is going to change how reionization happens. So when you measure the Lyman alpha force, you know that you have to have enough megaparsec scalar power in Lyman alpha force at redshift 5, for example, to explain the observations. And if you have a very small mass, you wouldn't have this power because you wouldn't have the halos that are able to host this Lyman alpha, the hydrogen and the Lyman alpha. So this puts one of the most stringent bounds that we have on the fuzzy dark matter mass, which is 10 to the minus 20 eV. It has to be bigger than that. We can also use a 21 centimeter. We have here bounds for the global, but in the future we are hoping to use also the perturbations in the 21 centimeter brightness temperature, which also puts bounds. We can also use other probes of small structures to measure the suppression. We can use probes like stellar streams and gravitational lensing, which are very good gravitational probes. So they are very good to check the existence of small scale structures. We can use, for example, strong lensing for that. Or we can use stellar streams, which are these streams that you have, which is a disrupted globular cluster, for example, that go around our galaxy, in the outskirts of our galaxy and going around. They are very prolonged objects. And if they see a dark matter halo, for example, you're going to see a break in this stream. So you can actually try to see the stream and see how many breaks I see in the stream, to try to probe how many small-scale structures this stream found in its way in the galaxy, in the halo of the galaxy. We have one measure of this using the stream called GD1, and it actually tells us it's compatible with CDM. But this is a very new field of research which is being developed now, and it's going to be an important probe for these ultralight dark matter models. So this also puts a bound here on the possible mass of fuzzy dark matter. We could use dynamical effects like dynamical friction and heating to put other bounds here. I don't have time to talk about it, but you can also put not the strongest, but good bounds on this. Or you can use the presence of a core, the fact that those models predict a core inside of the galaxies, to try to put bounds on the mass. And how do we do that? For example, in the strongest bounds that we have to date now on the mass of fuzzy dark matter are given in this article with me and my collaborators, where we use ultra-faint dwarf galaxies, and we try to fit in those in the kinematic of those stars in those ultra-faint dwarf galaxies. We try to fit this profile which contains a core. So by using the data of 18 ultra-faint dwarfs, we try to see if the data in these galaxies allows for the presence of a core. And with that, we can put bounds on the mass of the fuzzy dark matter. And here I show the bounds for the 18 ultra-faint dwarf galaxies. But one of them, SEGI1, gives the strongest bound to date that we have on fuzzy dark matter, which is that it needs to be around 10 to the minus 19 eV, which is here more or less in the allowed region for many of the observations. So the presence of a core also allows us to put very good and very strong bounds on the mass of fuzzy dark matter. But there's a problem, as many of you might have noticed. The last row shows dwarf spheroidal galaxies, which are still dwarf galaxies, but they are much larger dwarf galaxies than the ultra-faint ones that we used in this analysis. So if you have these luminous dwarfs, like Fornax and Sculpture, and you try to do exactly the same thing, you try to fit a core in the interior of this galaxy using the movement of the stars in this galaxy, you actually see that while all of these other bounds tell you that the mass needs to be bigger than a certain value, this bound actually tells you that they expect to have a very small fuzzy dark matter mass. So they expect to have a very large core inside those galaxies, while if you have here for the ultra-faint dwarfs, if you have a very large mass here, 10 to the minus 19 eV, you're predicting that those galaxies have a very small core. So those dwarf spheroidal results, they are not compatible with any of the other results that we have. This result should be not taken too seriously. This is being revised. So if you exclude this result, it really it doesn't match any of the other bounds coming from all of these other observables. So this is a big mystery that we have now in the fuzzy dark matter. If you exclude this, you would see that we're doing really well on constraining the fuzzy dark matter. So this dwarf spheroidal, this luminous dwarf spheroidal, they are a puzzle for the fuzzy dark matter at this moment. There's incompatibility of this bound with the others. And there are many possibilities for this incompatibility. As always, we're doing those simulations with dark matter alone, so baryons could be influencing this, and especially those dwarfs, they are very luminous, so the influence of baryons is expected that they are going to be more influenced by baryons. So it could be that baryons are playing a big role here. Or it could be that we're trying to use a universal core profile for all the galaxies that we have. And we know that our galaxies in the universe are very different. They have very different masses. They have very different formation histories. So maybe we cannot use universal core profiles. But anyhow, this really places a challenge for the FDM model that we need to solve. So in an ongoing work that I'm doing with my student, we are testing the universality of this core profile. So we're testing how universal it is, the relation that we use for what is the mass of the core giving the mass of a halo. So can I predict this? So what we use nowadays for this, it's based on a simulation by Shiv from 2014. That it tells us that the mass of the core is related to the mass of the halo by this relation. But other simulations already started to show us that this is not true. And if you have a difference in this relation, you will have a difference for the mass that you infer when you're trying to fit a core to the galaxy. And what we have been showing this article that is going to be out next week, so I invite you all to see, is that actually this profile, so here's density over radius, these profiles are very, you have a huge dispersion on them. You can also see here's the mass of the core over the mass of the halo. And the relation that is used nowadays is this black one. And we can see that there is a huge dispersion here around this. So you cannot use this relation for all the galaxies. So this relation is not universal. And this can really change the mass that you infer from those galaxies. It can change them by 50% or more. So yeah, this is a new study that we have been doing with our simulations, which are one of the most precise, and we have biggest amount of simulations in the field now. So this is the status at this point of the fuzzy dark matter. we can definitely exclude this 10 to the minus 22 EV, which would be the mass that this model would have to solve all those small scale problems. So this model doesn't solve the small scale problems in this way, but it has a very rich phenomenology, and that's why we study it. But also we have still this this challenge here. So although we are narrowing down on the mass of the fuzzy dark matter, there are still some challenges to be obtained. And I think we're doing this nowadays, but the future is really bright. In the future, we're going to have observations that are going to improve a lot in all of those bounds that we're showing here. And I'm going to talk a little bit about two of them, the PFS, the prime focus spectrographs, and BINGO, which are two that I'm part of. So PFS, the prime focus spectrograph, is going to be the spectroscopy part of the Seminário project. And it's going to be very good for measuring dark matter. So PFS has three different science goals: galaxy archaeology, cosmology, and galaxy evolution. And different properties of dark matter are going to be being measured in each of those science goals. So you have a very strong synergy between each of those science goals. But especially the galaxy archaeology, galaxy science goal, it is the most important for those models, because we're really going to improve and do a unique search for some of the Milky Way dwarf satellites. Also, we're going to measure the M31 halo. We're going to measure stellar stream. We're going to measure Milky Way halo, and all of that can be used to put constraints on the fuzzy dark matter that are much more precise than the ones that I showed you. So PFS has a huge potential for probing those ultralight dark matter models, and actually many different dark matter models with a lot of precision. We can also use 21 centimeter cosmology. So we have a telescope here in Brazil. Here, I'm not in Brazil, but there in Brazil, which is the BINGO telescope being built in Paraíba. So with 21 centimeter, we are actually probing the amount of hydrogen that we have in our universe, which is a bias probe of the dark matter distribution. And since those models have this suppression of the power spectrum on small scales, not only we can measure this suppression of the power spectrum on small scales if we are able to measure the power spectrum in those scales, but also since I only have halos, the biggest halos in the universe now, all my hydrogen is going to be on the biggest halos. So this is also something we can measure with 21 centimeter experiments. And BINGO is one of those experiments, which is this single dish, actually has two dishes, experiment in Brazil, and it's going to be able to put interesting bounds on fuzzy dark matter. For example, here I show a bound on the amount, on the abundance of this. But these are only two examples. CMB, the future CMB are also going to improve a lot of those bounds, especially by measuring reionization, which we can do by improvement on the bounds on the optical depth and the kinematic synapse-Eldovich effect, because again, since you don't have the smallest halos, you change how reionization proceeds, so this can be probed. This is going to be probed in the future. But all of these bounds that I talked to you about until now are only gravitational bounds. So I'm only considering measuring this using the large, intermediate, and small scales. You could also consider that this axion or axion-like particles interact with photons. And for that, you have a huge amount of other probes that are also probing those axions in other mass regimes. So with those direct and indirect detection experiment, plus these gravitational experiments that I'm proposing here, we are going to be able to really exclude the max range of exclude or detect, if we're lucky, this mass, a huge mass range of the possible axion. Another improvement in the future that is going to allow us to constrain those models even better are in simulations. So we, at the moment here at the Max Planck, we have the biggest simulations done by Simon May and Volker Springel. My group has the most precise ones, the ones with the biggest precision. But we are also investing in simulating the fuzzy interacting dark matter model. All of the simulations I showed you are only for the fuzzy dark matter model. This is the simplest one. There are only a few groups that are modeling, have simulations of this model, and we are one of them. And from this preliminary result, we can already see that they predict very different structures. So this might be an interesting thing to probe. And we're also looking for those vortices in simulations, as I won't have time to talk about this, but in the future, this will be probably another way that we can try to probe these models of dark matter. And last but not least, we're inventing new probes. We're inventing new ways of probing the smallest scales. For example, we have this idea by Cord Vorking and collaborators on how to probe to get information of the small scales in the power spectrum using the convergence power spectrum. So we can also think about different ways of probing these small scale structures that are going to allow us to put good bounds on these models. As I said before, I won't have time to talk about the superfluid dark matter model, but this is a very interesting model, and I'll be very happy to answer any questions. And just a reminder that those ultralight fields, they could also behave as dark energy. So if you have a mass, if the mass is smaller than 10 to the minus 30 or 32, those models behave like dark matter. So the axions that we're talking about now, exactly the same model, they're going to be models of dark energy. And this can also be probed by many of the probes that I showed. We can also have, in these models, they always also give us like unified dark energy models where you can have dark matter and dark energy being explained by it, that can also be probed by future observations like PFS bingo, but also many large-scale structure and CMB observations. And also we can, if the axions behave like dark matter, we can also try to probe different observables that we thought we wouldn't be able to probe before, like probing cosmic birefringence from axions. So because axions have this parity violating physics, they are going to change the polarization angle that we have. They're going to rotate the polarization angle of the CMB. And so those models of axions that behave like dark energy, they provoke this. And we have recently measured this angle with a small statistical precision, but we have measured it by Minami and Komatsu. So this also gives the possibility of probing these axions in the regime where they are dark energy. So I said a lot of things, a lot of information. So I'll just leave you with my summary here because I'm over time. So thank you very much.
So thank you very much, Elisa, for this beautiful talk. I invite everyone to open the microphone to thank Elisa for the great talk. So thank you. So with that, we have time for some questions. And if you want to ask a question, please just write in the chat or raise your hand. So in the chat, just to say that Professor Zanelli at some point had to leave, and he just wrote great seminar, Elisa. Thank you so much.
Thank
Muito
you.
obrigado. So Eduardo has a question. Eduardo, you can just unmute yourself and ask.
Sure. Can you hear me?
Yes.
Okay. Well, first, thanks for the great seminar. I found it was very comprehensive, and there were lots of phenomena with dark matter that was not even aware about. I have just a small curiosity about the part that you mentioned about ultralight fields that could behave as either dark energy or dark matter. In particular, that graph that you showed in the beginning, in which it converts from a dark energy behavior to a dark matter behavior, which looked very interesting. And I was wondering, do you think it could possibly have any cues in solving the Hubble constant problem and Hubble constant tension, and such that you could switch and a different way that expected the dark energy portion and the dark matter portion of the universe?
Okay, so let me just go back to that plot. You have a lot of slides. Okay, so here, right? So we have this behavior that depending on the mass, you're going to behave like dark energy or dark matter. So one thing is, so those models can actually behave like dark matter or dark energy, but not both. Not both, unless you have something special. So as soon as you fix the mass of this model, the mass of this model is going to tell you if this is going to behave today like dark matter or like dark energy. And this is also going to tell you if you can have 100% of this being dark energy or dark matter. So for example here, if the mass is bigger than 10 to the minus 28 eV, this will start oscillating before matter radiation equality. So this will behave only like dark matter. You cannot have the behavior of this as dark energy today, only in the past. And the same if it's dark energy. So this plot here shows quite well. So those are the bounds. So those are the bounds that we have in those models. So this is the fraction of axions in the dark sector, and this is the mass. So all of that was talking about dark matter being 100%, so being 1 right here, 100%. It is for masses that are bigger than 10 to the minus 25 here, right? So these are constraints that you can put with CMB and large-scale structure. So then you can tell me, so if I have something in the mass here, so it is behaving like dark matter today, but it started behaving like dark matter really close to matter radiation equality. So maybe this could solve the Hubble tension. Actually, we still cannot figure out how, because you can only have a small amount then of these axions if they have this mass, because they really change a lot the power spectrum, so they can really be constrained. The influence they can be constrained. So can only have a small fraction. And then when you go back to the dark energy region, you can have more of them, but then you're explaining dark energy today. So having said that, it's tough for them to explain the Hubble tension in this way, because you can only have a small fraction. But there are many models that try to use ultralight fields for that. So the early dark energy model, for example, is one of them. It is not exactly this model. It has has a very similar potential that what we have. So we had, so let's go back here to the axions. So here the axions have a potential that is 1 minus cosine here, that you can expand, being like a mass plus an interaction. So the early dark energy needs to have this early dark energy period, and then it needs to drop down and not even behave like matter. It needs to really drop down the density right after recombination. So it has to act between matter radiation equality and recombination, and then it has to drop out. And the way they do it is they put this potential to the power of 6 here, or other powers, right? So it's not exactly the same model. It is still a light field, but it's not a dark matter model today. It is very fine-tuned in some sense, right? You have to tune the potential, you have to tune the initial conditions, you have to tune the decay. So yeah, you can have those models. You can cook up maybe a way of those models explaining the Hubble tension, but not only it's very hard to explain the CMB and the large-scale structure today, but yeah, they are still very phenomenological in that sense, because the normal axiom doesn't work for that. You can also have unified dark energy potentials, unified dark energy models using this. So, for example, this model that we had, it is possible to construct using this type of ultralight axioms. A Lagrangian like this that behaves like dark matter and dark energy at late times. This gives you a slightly different evolution of the universe, but again, it's very hard to explain the Hubble tension, because this, when you modify early time physics, this is very constrained then by large scale structure. So yeah, so it's very hard to do that with those models. But that doesn't mean that you don't have them in that literature. They are just very constrained.
Okay, thank you very much.
You're welcome. We can talk more about it if you want to send me an email. We are working on those things now. So.
All right, thanks.
Okay, thank you, Eduardo and Elisa, for the discussion. I see that Leila has raised her hand. So, Leila, please.
Hi.
Hi.
Thank you for the nice seminar. I always like to hear your seminar.
So, sorry, Leila. I mean, your volume is a bit low.
Oh, sorry. Better now?
Yes,
Yeah,
much
way
better. Yeah.
Can you hear me?
Yes.
Yeah. Okay. Elisa, my question is, how do you, with cosmological experiments, how do you test the presence of a condensate inside a galaxy?
Yeah, so you won't be able to use cosmological perturbation or cosmological observations. You would have to use observations of the halo. And it's actually tough to say how would we test this, because so let's say we have a condensate in the middle of the Milky Way, for example. How would you test that this is a condensate here today? So what does it mean to be a condensate for us here? So what would change in our dynamics, right? And what we measure, what would change in how the stars behave and everything. So I think the way we do it is by trying to see this friction and heating, different behaviors, but it's still an indirect probe of a Bose-Einstein condensate, right? So this is a very tough question to answer, and I don't have an answer. What we have been doing now is we have been trying to theoretically and numerically prove that we have the conditions for condensation. And another thing that you can say is that if there is a core inside of the galaxy, this core, if it is a condensate, the field is in the lowest, in the ground state, yeah, in this core. So can you prove that? You can in simulations, and we actually do that. So in the simulations that I showed you here that we have, we actually probe the field here, and we see that it is in the ground state inside. But is this a proof that is a condensate? It actually is a bit harder. It could also just be the lowest the K equals 0 mode of a classical field.
In any case, you prove the possibility that it can be
Yeah,
compatible with a condensate. Yeah.
exactly. That's all we have been doing now. So yeah, I think we're open to ideas in that field. We're open to ideas in that sense. What would be yeah, so one of the things that could be that are definitely something that would tell you that there is a condensate is if you see vortices. So those vortices in self-interacting fuzzy dark matter, they only appear if you have a condensate, if you have a superfluid. So if you see them, which is very hard to see, we still don't know if it's possible to see. This will be telling you that you have a superfluid. But we have been seeing simulations that you can also see vortices outside, in the outskirts, in the NFW profile. So it's very tough, Leila. If you have ideas, that would be great, because we are still, all of those wave-like behaviors, like the wave interference, also vortices, formation of condensate, all of those we're still thinking of how to probe them, how to see them. Even the interference patterns, we don't know how to see them.
I see. Yeah.
We don't know how we could probe them.
Yeah, but having several predictions at the end, maybe you have a good sign of it or not.
Yeah, the problem, the ones we have now, they're very degenerate with other things, and they could be generated by other effects that are not either condensate or a wave interference or something. So it'll be interesting to, yeah, this is something we have been doing lately. We have been trying to figure out ways that that would tell us, yeah, I can measure, or I can say that this is different than other, yeah, other measurements, and this is definitely because this is a wave or something. Yeah, because all these suppressions of structures and cores, they are very degenerate with, for example, what baryons could do, what other dark matter models could do. Self-interacting dark matter also predicts suppression. Warm dark matter also predicts suppression. So I think the challenge of those models is, it's beautiful the way we can probe those suppressions of structures and those cores, but they are degenerate with those other suppressions. So how can I disentangle them? And one way would be by measuring this wave interference or measuring these dynamic effects like condensation. But we still don't know how to measure them. So it is an open question, and a very good question, Leila.
Thank you, Elisa.
Thank you.
I like very much your seminar.
Thank you
Congratulations.
so much. Thanks.
So thank you, Leila, for your question, and thank you, Elisa, for the answers. I don't see new questions in the chat, and also I don't see any raised hands. So I'll take this opportunity to ask a question myself.
Yeah, of course.
Yeah. So I have some questions, but I can write to you later. So
Yeah,
I will
please.
just,
And this is also for everybody.
yeah.
I would love to discuss with anybody. So please write to me if you have any questions. Yeah, but please go ahead. Yeah.
Yeah. So I was just wondering. I mean, just thinking from a field theoretic perspective. So you have a field that is ultralight, interacts with gravity, and perhaps self-interactions. And you say that there is the possibility of having a condensation. So I'm just wondering, from the pure field theoretic perspective, if you can really show that such a system can condensate or not, in the usual sense of let's say, statistical mechanics. So and typically this comes as a phase transition, and phase transitions typically have scaling exponents that are things that you can measure. So I'm just wondering, I mean, maybe my question is too naive. I'm just wondering if you have such a scalar ultralight field that self-interacts interacts and interacts with gravity. If you can probe, I mean, at least using the standard techniques of statistical field theory, that there is a condensation.
So the reason why we think there is condensation is because we do the naive quantum field theory calculation. So what are the conditions for condensation? Is thermalization, and also this field, it needs to be in thermal equilibrium, your halo, for example, or your system. And also it needs to go to the ground state, right? You have to calculate this ground state. And you can do that using many different techniques. So we do that in the field theory that we have to describe this, and we show that it is possible. But there is a problem. So we're doing this. So today, the actions and everything that I'm describing here in the halo, it is quite classical. So everything is classical. This field is behaving and evolving classically since after inflation. And because of the high occupation numbers in galaxies, this is also a classical field. So all of this description is classical. So there is already the first question. Can I have condensation in this sense then? I can show that I can have thermalization. Can I have condensation? Or do I have a moment where this classical this classicality breaks in this evolution, so I can form a condensate, or I don't need that. So, for example, these simulations are done using an analogous classical model for condensation. So, for example, these analogous classical models, it is just like it is a wave, a bunch of waves. So you use this ensemble of waves with interactions between them, and this describes the Schrödinger equation, for example. But for example, this is a classical analogous of a quantum system. So for example, the statistics, it is the wrong statistic. It's not a Bose-Einstein statistics. It is actually a classical statistic. So it has a UV divergency. So what you do, you just like cut off this theory to describe. So all of the proofs that we have that condensation happens, they are either in field theory or using this method here, which is using this wave turbulence framework, but they're all classical. And to be able to get a distribution that kind of fakes a Bose-Einstein distribution, you put a cutoff in the velocities or in K. So you're proving condensation with a classical analog. You're not doing like a quantum mechanical calculation, right? So this begs the questions, am I doing the right thing, right? Am I doing the right calculation? And am I proving the right thing? I'm proving in a classical analog something that should have a quantum origin. The distribution is different, but I put a cutoff here. You know, like it's even in field theory, it's complicated to show.
Yeah.
And and also the best way to show condensation would be show that this is in the ground state. But what is the ground state of a halo? That's another question.
Yeah. So I mean, I was thinking more in a, let's say, in a toy model, that you just have scalars with the potential that you want to.
Yeah, that we do. That is the prototypical example of condensate.
Yeah. But now you have a non-trivial background, right? I mean, you have to put that on a dynamical background, and this can be catalytic or not to the condensation.
Yeah, we can calculate this, and this is those calculations here. You know, those are, for example, you're calculating how much time it would take this condensate if I'm in this toy model of a classical field, of a scalar field with a small mass with this potential. But again, it comes up to a classical versus quantum discussion here. you can do an analogous classical description of this and reach the conclusion of condensation. But is this enough? If I do the fully quantum calculation, you can do it, but then I ask you, this field is always classical, so what is going on, right?
Okay, yeah,
This
no,
is
I
an open
understand that it's very
question.
tricky, yeah.
Yeah, it is an open question, and we are really looking for an answer. And if you have an idea, like Mark Hertzberg from Tufts have been working on that as well. So he has been working about the coherence of those fields. Is it really, they are really decoherent, or they could maintain coherence? So yeah, there's some works on this. We're trying to answer these questions, but yeah, it's a bit complicated. Maybe we're seeing this in the wrong way, and you have a good idea.
Yeah, it would be nice to chat about that.
Yes, definitely. This is, I think, one of the biggest open questions of those models. Yeah.
So Anderson is sending a message that he thanks the seminar. So the message just closed. So thanks for the excellent seminar, Anderson says.
Thank you.
And Caio, Professor Caio raised his hand while we were discussing. So Caio, go ahead.
Sorry, it's just a quick question about these structures that you mentioned, this condensation.
Yeah.
So what would be the density? I mean, the expected density of this condensation, and also the size. Do you
Okay,
have an
so
idea?
yes, of course, we do. I'm thinking where I can show you this better. So first, we know that the condensate needs to be in this region, inside the Jeans length, because this is where the only region where I have a stable solution, right? The solution outside is unstable because it has gravitational collapse. So it has to be at least smaller than the Jeans length. I don't show here, but we also have calculations that show that they should be of order of the de Broglie wavelength, because this is actually, so what is this region here? This region is the ground state of my field psi. And the density expected, it is psi square. So, I have it here. No. Yeah, so the density is m psi square, right? So this is the density, but I'm in the ground state. So I have to get the ground state of my field psi, and the density is going to be given by this. So this is what these simulations are doing, actually. So here you just calculate the field. And then you see if the field is where the field is in the ground state, and you can find the field in the ground state in this region. And we expect this to be smaller than the Jeans length, but of the order of the de Broglie wavelength. This is what we call the solitonic core, because it is the core inside that galaxy, but it is a soliton, which means it is the ground state of this system. So that is what we expect of the size and of the density.
Okay, so this is very similar to the oscillatons, right? That people mention.
Oh yes, yeah.
Because I mean they are essentially the same, I guess, right? You have a structure formation from a very light field, and you compute things there. I wonder if you consider additional components of ultralight fields, because I remember that there are some, because you mentioned that this field grows to the fundamental state, right? But as far as I can remember, there are some papers that shows that if you have some additional components, like a pair of light fields, one of them can live in the excited state, and I mean, and because you have this additional component, I mean, one kind of stabilize the other or something like that.
Yeah, yeah, definitely. And we have this a lot in condensed matter, right? So if you have more than one component, you can also condensate in a mixed state of one being excited and the other being. So what does this mean is that your ground state will be different, but you can still have the condensate.
Yeah.
And this can help. This field, like you said, can help stabilize. It can help many things. So yeah, you can definitely have that. We are not considering here, we're considering the simplest case, but I think we're starting now to consider more than one field, more than one axion, more than one light field around. Yeah, you can definitely have that. And this wouldn't impact condensation in a sense that it can still happen. It's just going to be in a different ground state. And for example, this time of relaxation will be different, right? And maybe you will have more interesting structures as well. But we're still so puzzled about this that, yeah, so.
In your case, this field is real, is it?
No,
It's
it
not,
is a
it's
complex
small.
field. Yeah.
Yeah, I see.
Yeah.
So it's like a boson star then.
It is a boson star. So a boson star is only a different name for a soliton.
Okay.
So a boson star, it is a solitonic core that is only created by gravitational collapse.
Yeah.
If I have also self-interaction, then I call this a soliton. So they are the same thing. They are a collapsed structure of ground state. I would say maybe it is ground state object, right? Yeah.
Okay.
It's tough because we're trying to make a parallel with the condensed matter literature also. So I think you're right. The best way of saying is like, if you only have gravity acting, this is a Bose star. If you also have interaction, you call this a soliton. But
yeah,
those are...
I mean, those names, I mean, they are very confusing.
Yeah.
Because some people, I mean, like you said, they call solitonic stars and
those solitonic stars, solitonic cores, exactly.
Yeah, then they also have these bosonic structures made by vector fields, and then they call Proca star and sometimes vector boson stars.
Exactly.
So it can be kind of confusing, this kind of thing.
Yeah, in my review, I try to really like say, okay, let's call this. But we know that physicists, they have habits, so it's going to be hard to break. So it's only important that we know that this is a ground state configuration.
That's right.
Of your system, yeah.
Even the same, I mean, the same. Myself, I sometimes I change
Me too.
from one paper to the other. I change the name a bit, but
yeah.
I'm not helping. That's the point. Okay.
I completely agree with you. I'm adding to the confusion of the literature. Yeah, it's because just using solitonic core, solitonic star is so usual that yeah, we end up. Yeah, but thank you for pointing this out. It's true. Yeah.
No, thank you.
Thank you.
Okay, thank you, Caio, and thank you, Elisa, for the discussion. And I guess we have to stop here. Otherwise, the people in Brazil will just starve.
Yeah.
And yeah, so let's thank Professor Elisa again.
Thank you very much. I want to put this nice picture of Munich for you.
Very nice. Okay. So I will stop the recording now, and let me thank Elisa again for this great talk and for the great discussions. And I hope to see you again in 2 weeks. Okay.
Okay. Thank you very much.